Hello. Can you hear me, guys?
No, sir, no question.
No questions.
Sir,
Yep.
I actually had one, but I couldn't solve all the problems of the fundamentals of physics. So, can I ask that question in the next class?
Sure.
Okay. And sir, if I had any problem, can I inbox you directly?
Yeah, you can give me a
Oh,
message
thank
in
you,
the
sir.
Slack actually.
Oh, yeah, yeah, okay, sir.
All right. So then we should start our topics today. So today, basically, we are going to talk about uh, motion in 1D, 2D, and also the 3D. We will start that step by step. Fine. So let me allow to share my screen with you first. All right. So you can see my screen, right?
Yes, sir.
Fine. So we're going to talk about today motion in 1D and the 2D. We can say an object has a motion when it is basically the moving, right? So that means when it's basically is changing its position. So that motion we can categorize in the two way. One, we define, say if we write that motion, we can categorize in the two way. One is we define, that is linear motion, linear, or sometimes we also say that translatory motion, translatory motion. And second one we can say, which is rotatory or circular motion. Mostly we are going to talk about the linear or translatory motion in this class, and rotatory or circular motion we'll introduce that part in the later. And mostly in this linear motion, we are going to, linear motion is basically when the particle or the system is moving in a straight line or in a line actually. So mostly we are going to talk about the mathematical description of the particle. We will describe over here. So that's mean what would be the particle, what is its location, what would be its velocity, how much distance is going to travel, etc. We are going to define what would be the acceleration, what would be the velocity, instantaneous velocity, average velocity, and a lot of things we are going to talk about over here. That would be in terms of mathematics, and that is known as a kinematics of the system. So kinematics actually will define that mathematical description of the system. And remember, this system I am defining over here, system in physics we define system is anything which is in my under investigation. So that means that any object which I am closely observing, or if it is in my focus, in another word you can say that actually that would be the system. Anything in my under investigation, that could be my system. That's the way we define in system in our physics. So that's why I'm saying that any system that we are going to describe over here, that would be totally the mathematical description of the particle. Not why it is changing its velocity, why its acceleration is changing. That would be defined by the dynamics of the system. And for that one, there would be another thing actually, which is required. The force would be the required to describe the dynamic of the system. Since we didn't introduce that idea of the force, we will not talk about that dynamics of the system, because for that one we need to introduce the idea of the force. We'll talk about that thing after introducing the Newton's law, three law of that one, Newton's law of motion. Then we can describe actually that dynamics of the system. But right now we are only going to talk about the kinematics of the system, which would be the mathematical description of that system. All right, to describe that kinematics of the system, first we are going to define some parameter, you can say. So one, we can define the position. Position, actually the location of a particle at any particular time. Say if I consider in Cartesian coordinate system, which is very much familiar to you, say this is my x and y, say a particle is over here. So now if I want to express that particle is over there, then the location of that particle or the coordinate, you can say that x and y, right, the coordinate of that particle. If I want to express the position of that particle from my origin or a reference point, then definitely I can say this would be that location of that particle, right, which
Yes, sir.
I can express by a vector. That vector generally we express by that position vector r, and that position vector, now I can write this position vector would be, it would be x I hat plus y j hat, right, because I know that r is basically nothing, which is the, if you express this is, again I am saying that, which is actually the vector triangle law. This is my x I hat vector and this is my y j hat vector. They are head to tail connection over here, so that's why I can say that r would be the position vector would be of that particle, where x and y actually the coordinate of that point where the particle it is. Now say that particle change its position in a time from, say, that point P, which I express right now, say this x1, say that y1, at a time say that it's changed its position Q, which is x2 and y2, say that is actually, say that displacement. Or I can say the particle traveling in a curvature path, actually, if it is travel in that way. I'm sorry. Say this is actually the traveling path of that particle. So in a particular amount of time, the particle was point P, and another time, after a certain time, it's a position actually the Q2. Then I want to know what is the distance between these 2 points, right? So, or the displacement, I'm going to talk about first displacement. What is the displacement of the particle in that particular amount of time? Remember, displacement is a vector, and that vector I can write, this one would be del r. Say that this is actually that del r. Now I'm going to find out. Say this one, if I draw a axis over here, say this is my reference point, Cartesian coordinate, and say I express that point P is a position vector, and another one is Q, I express by another position vector. That position vector, I can say this one would be basically that R1, these two would be basically that R2, right? And that particle which travel from point P to Q, that would be its displacement from P to Q, right? That one I want to find out, which is the displacement. It's the shortest distance between the 2 points. Now, if you closely observe from this diagram, which in your Cartesian coordinate system, then I can write this position vector of the particle at the initial point, which was P. I can express this would be R1 x1 I hat plus y1 j hat, right? Can you write this one again using the
Yes,
vector
sir.
triangle law?
Yes,
Then
sir.
yeah, any question over here?
Sir, I don't understand this.
Which
Can
one?
you please?
Which one?
This is the last one.
Last one means Say the particularly last one.
The r vector, the del r vector.
The position one.
Oh, del r.
Yes.
Del r actually the distance between these 2 points P and Q. That one I want to find out. I just expressed the del r. Still I didn't find out the del r.
Yes, sir.
Did you get my point? Alright, so I'm going to find out that del r right now. So first I express that r1 with respect to my that origin. R1 could be written as x1 I1 plus y1 j1, right? Sorry. So which is I and j actually the unit vector in Cartesian coordinate system. Now r2 I can also write down, which would be x2 I hat plus y2 j hat, right? Now look at this. These three vector r1, r2 and del r in such a oriented that they are head to tail connection at the point is over here. The head of the r1 is connected to the tail of the vector del r. Then definitely I can write r1 plus del r must be equal to the r2. Can I write this thing?
Yes, sir.
Then I can write this del r. Del r is going to be r2 minus r1. That's the displacement between the point P and Q. I want to find out. Now I know that r2. So r2 is basically x2 I hat plus y2 z hat minus x1 I hat plus y1 j hat. Right?
Yes, sir.
Yes, sir.
Then I'll just separate this equation that I can write x2 minus x1 I hat plus y2 minus y1 j hat. So that would be the displacement between that point P and Q, which is actually we subtract that coordinate of that one, right? X2 minus x1. So x2 actually the final position, because I am going from P to Q. So this was my P point and this was my Q point. Q point coordinate was x2 y2 and P was x1 y1. So when I am writing this vector PQ, which is actually the del r, so I'm subtracting final point minus initial point, x2 minus x1, right? X2 is the final point, which is actually the PQ vector. I can write is a PQ vector. But if I write the QP vector, so that's when I'm moving to the opposite direction. So that's why it has to be defined in that way. It's a vector. We discussed this thing in the previous topics, right? Fine. So that's why the del r, which is the displacement between these 2 points P and Q, we can express in that way. If it is three-dimensional, there will be one more component, which would be the z component. And remember, since displacement is a vector, it has some magnitude and the direction. If you take only the magnitude, you will find out the distance, which is a scalar quantity. Remember this thing, that would be the magnitude of this displacement vector. You can find out in that case the distance. Fine. If I know the displacement, now say if I want to find out that velocity, I can find out. So velocity we define the rate of change of position, right? Is a general definition. We define the velocity, which would be rate of change of position. So then we can define that velocity. It would be del r over del t, right? Meter per second. Del r actually the change of position that we find out over here. That will, if we take the ratio del r over del t, that will give me the velocity. If I want to find out that acceleration, then acceleration is rate of change of velocity with respect to time. So that I can write it would be del v over del t. Its unit would be meter per second square. So that's mean if you just know the position, then you will be able to find out the displacement. If you are able to find out the displacement, then you can find out that velocity and as well as acceleration of that particle or the system. So although in everyday language we do not make any distinction between the speed and the velocity. So, but in physics it has some difference between these two quantity, velocity and the speed. Velocity is a vector, speed is a scalar quantity, remember. So, because this has the two different characteristics actually. So, that is why if you can say the speed, that would be only the magnitude of that velocity vector, right, which has no direction actually at all. So, speed is basically, you can say how fast actually
Is it magnitude or distance?
which one
Sir, speed.
is a magnitude of the velocity. So, speed is basically how fast a car is moving, you can say, whereas its velocity is how fast in which direction it is moving. That would be that velocity. Fine. In general actually you can say that a car is basically, or a object is speeding up if V and A are in the same direction, then you can say the car will be speed up. A car will be the slow down if V, velocity and the acceleration in the opposite direction. Then you can say the car is going to be the slow down. A car will be at a constant speed or the constant velocity if your acceleration is 0. These are the general characteristics. We will talk about this thing. All right, so now we are going to talk about another parameter, which is we define that average velocity. Say you are driving in a road with your brand new car and your speed is say that 25 meter per second. It's only for say to understand, you can choose anyone, any speed. Suddenly when you are driving, a pedestrian actually come in front of you. What you did, you press the brake and suddenly instantaneously your car fall the speed from 10 to 25 to 10 meter per second. So that's when you slow down the car and that pedestrian cross your car and again you speed up say that 25 meter per second. You come back to your original speed again. And if this total scenario happen in say only for calculation, I assume in total is thing is happen in say that 1 second, although it's not possible, right, but say only for simplification of the calculation I think about is take the 1 second. Then if I asked you what would be your average speed when you are going to slow down your car, probably you are going to say that it would be 25 plus 10 divided by 2, that would be 17.5 meter per second, right? If I asked you what is the average velocity of your car when you slowing down to the first half of that scenario, and it is also the second half, it is also the same 10 plus 25 divided by 2, which is 17.5 meter per second. Look at this. In your total scenario, in that between, you never your car has never the speed of 17.5 meter per second, right? So that's why I'm saying that this 1 second over here. When it was initial speed, if you think about this is your initial speed, it was 25 meter per second. Your final speed, then is the 10 meter per second. In between, you have never that the speed was 17.5 meter per second. It is also the true for in the second half, right? So that's mean average speed is basically is not a actual scenario of your journey, but it is important. Why it is important? I can say, I can make a guess what would be that. Say if I say in the second half, you can say if you move at a 17.5 meter per second after a certain time, starting from that 10 meter per second, after a certain time you will acquire that speed. You can check that if you use your law actually, which is v equal to u plus at, then you can find out, right? So what would be that? V, if I let initial speed is 10 plus a, I can find out, which is 25 minus 10 divided by t is acceleration into time, that t will be cancelled out. Then you can find out that v actually, which is 10 plus 15, that's going to be 25 meter per second, or unit, whatever you use over there. So that's mean average velocity is basically a projection how you are moving. If your average speed is high, you will cover that distance in a short amount of time. If your average speed is low, then it will take higher time to cover up the same distance. So that's why it is important for us actually the average velocity, or ever the speed. Average speed is basically the magnitude of your average velocity. Now, how we are going to find out that average velocity? Say mathematically, say I'm going to draw again that interesting thing. Say this is a case I'm drawing. So you start from that point. So this is actually xt1. You start from there your journey with your brand new car, and say this is x2 distance, this is xt3 distance, and say you come back, then this is actually say that xt4 distance, and again you come back to your origin, say this is actually xt5 distance, and this is also the corresponding time. So this is t1, this is t2, this is t3, this is t4, and this is actually that t5 time. You come back to your original position, and say I choose this direction is the positive x direction for simplification, only for the calculation. Now average velocity, remember this is a general definition of the average velocity. Average velocity, we can find out the mathematically the formula. Say I'm going to find out the average velocity in between any time. Say for simplification I choose the average velocity in between time t1 and the t2, that we can find out that displacement at t2 time minus displacement at t1 time divided by time t2 minus t1. Its unit would be meter per second. And since it's a one dimensional, I will use the I hat over there. Right? Do you understand this point? How I write? I write the definition, general definition of the velocity, rate of change of position which I give, which is del r divided by del t, because I am considering the time in between t1 and the t2, so that's why I take the first this position of the car at the x t2 time, which is x t2, and initial position at t1 time, which was x t1, and I divided by the time, which is t2 minus t1. Thus I find out that average velocity, and we express this quantity v, the average velocity, we can write the del x divided by del t I hat, and that would be del x actually the change, which is change. It's a very small change actually, we express in that way del x, so very small change, so that's why we write down in a del x over here. Now this one is a one dimensional. If it is two dimensional, then we can write it would be del x over del t I hat plus del y over del t j hat, right? If it is three dimensional, then you can write del z over del t k hat. So that would be actually the general definition of average velocity to find out that one. And this would be actually the most general equation to find out that average velocity. And this average velocity is basically it could be greater than 0, it could be equal to the 0, and it could be also the less than 0, depending on which direction actually you take that positive. So for example, if I say since I am moving towards that upward direction is positive, then I can say that average velocity in between time t1 and the t2 would be greater than 0, which is the positive quantity, right? But if I move in the opposite direction, say I can say that average velocity in between time t2 and the t4, then I am moving towards that direction, right? So that's why I can say that average velocity in between time t2 and the t4, it will be less than 0, because I am right now moving in the opposite direction. And if I say that average velocity in between time t1 and the t5, what would be that?
So average of V of T1, T2 and V of T2, T4?
No, the average velocity in between, just look at your definition actually, I write down. You
Yes.
say
It
initial,
will be 0.
it would be 0 definitely. It would be 0. Why it is 0? Because when you write down that formula actually, your final xt5 minus xt1, which is the same position, right? That displacement is basically over here at 0, because the point you start from there, that point, you goes and come back again over here. So that's when your displacement is 0. So that's why your average velocity is 0 in between time t1 and t5. You understand my point over here? It's a
Yes,
very
sir.
important thing.
Yes, sir. Okay.
Average velocity is 0 over here. What about if I say that average speed?
Total distance divided by total time.
Exactly. So if I say that average speed over here is not going to be t1
0.
and not t5 not equal to the 0, because average speed actually the total distance divided by total time. So total distance, if you say, so that distance, say for simplicity, that distance actually is goes the 5 meter. This is the 5 meter. Then it's come back again that 5 meter. So total distance in that case 5 plus 5 is going to be the 10 meter. And whatever the time it's saying, then you have to add that divided by that one, you will find out that average speed. But the average velocity is 0 over here. Alright, say now we are going to talk about, say that instantaneous speed instantaneous velocity first I am going to say, then the speed is basically the magnitude of that vector. Instantaneous velocity, I should start. So instantaneous velocity, actually that velocity just right after one point, say the speed at any particular moment. Suppose you are driving your car, in your car there is a speedometer, right? That you give that speed of that car at that particular moment actually. So that speedometer will be moved in that way. So at the moment you look at your speedometer, whatever it position in the meter, that would be the speed of your car or the velocity of your car at that particular moment when you look at that meter. That's called actually the instantaneous velocity. And this is changing at different moment, it will be the different, right? Fine.
Yes.
Now how we are going to find out mathematically that one, this instantaneous velocity? For that one, say I'm going to draw a curve actually of that journey I talk about over here. Say any arbitrary, say I choose, this is my y-axis, and say this is my x-axis. I am taking it is basically the one-dimensional over here only for this understand. Say this is my x-axis right now, there is a reason, and say this is my time over here in that axis. So I'm talking about that one that I draw for one-dimensional case. Then we will extend that idea also for the two-dimensional and the three-dimensional case. Say a car is traveling that one. Say I'm leveling this one. Say this is actually t1 time. This is actually t2 time. This is actually t3 time. This is actually t4 time, and say this is actually the t5 time. All right, say I draw that one. It should be t3. Say I draw that one in that way. So this is actually the position versus time curve of I'm going to draw it. And this is the way it's traveling. Then I can say this is actually your t1 time. This is would be your xt1. If you say this is actually t2, this is would be xt2, right? This is actually your xt3. Say this one actually your t4. Say for example this one is that point actually. This is actually t4 over here. That's fine. It's an arbitrary I'm choosing. Say I have the point over here, car is over here. So think about if I want to know the velocity of the car just right after that point over here, just next second, then what I'm going to do that one in that case, that displacement. So if you have say I'm drawing is a very to understand that one. So this is your location of your car. It's a big point, it's not that one. You want to know the velocity just right after that point, which I say I make a red circle over here. Your initial position is a black dot and the final point actually the red dot. You want to know the velocity in these 2 points, which is very close to your point. We can say that displacement is a very small distance, and it will time to travel from that black dot to the red dot is a very small amount of time, which is negligible. I can say that time would be del t would be tends to 0, very close to 0, but not exactly the 0, right? Then if you want to find out that velocity in that point, we can write the definition of the velocity, say final point which is xt plus del t, and initial point was xt, right? That's the difference between that 2 point displacement, and this would be time difference, which is del t plus del t minus t. It will ultimately give me the del t, and we define over here is a quantity which is, we say the limit del t tends to 0, right? Do you understand my explanation over here?
Yes, sir.
Yes, sir.
Now this quantity, which is I can write del t tends to 0, I can modify this one, which is write xt plus del t, which is my final point, and xt, which is my initial point, divided by del t, because t will be cancelled out from there. Now what is that? If you look, this is actually is a mathematical definition of the derivative of that point, right? This is actually the mathematical definition of the derivative of that function x. Then we define this v actually, which would be dx over dt, right? So that is would be actually the instantaneous velocity of that particle or the car. So that's mean if you know the position function of a particle or a system, if you take the derivative of that position function with respect to time, it will give you actually that instantaneous velocity of that particle. And you can find out that instantaneous velocity at any moment you want, just plugging that your desired time. So that's mean instantaneous velocity, the velocity at any moment you want to find out in using just, if you just know that the position function, then if you take that first time derivative of that position function with respect to time, you will find out that velocity, which is would be that instantaneous velocity of that particle. Then we can write down this thing also for 2-dimensional, also for 3-dimensional. I'll write so dx over dt is the I hat plus dy over dt into z hat plus dz over dt into k hat. So that will be give me that instantaneous velocity of the particle in 3-dimensional case. And if you want to find out the speed, instantaneous speed, you have to just take the magnitude of that vector, and you know how to find out that one, right? And this instantaneous velocity also could be greater than 0, it could be equal to the 0, and it could be also the less than 0. Now when say it will be basically the greater than 0, I hope you can understand that depend on the which direction you are taking the positive. For example, if I say, since I choose that direction actually, that positive, right, this one, then if I move towards that direction, definitely I'm going to say my speed would be, or velocity would be positive. If I move in the opposite direction, the velocity would be basically the negative. Fine. Now how I'm going to explain this thing from my this curve, say from this is actually that position versus time graph of your car.
By the tangent line?
Yes. Now if you look that from this curve, so I define that velocity, I find out which is actually dx over dt, right? This is the velocity. Say I drop down that I should that one. Now what is dx over dt from this curve? So from the mathematical point of view, you can say dx over dt basically the tangent of this curve. Am I right?
Yes, sir.
Yes, sir.
So that's mean if you know the position versus time graph, if you find out the tangent of that curve, that will give you the velocity. If the tangent is positive, I can say the instantaneous velocity will be positive. If the tangent is negative, I can say that instantaneous velocity would be negative. For example, I can say if I take the tangent at the point t1 and the t2, I will find out that tangent would be positive. If I take the tangent between the t2 and the t3, that would be also the positive. But if I take the tangent between the t3 and the t4, that's going to be the negative. Or any point, if you say the point t4, the tangent is going to be negative. Right? Also for the t5, you can say in that way. Fine. Now, why it would be the 0 actually? To find out the 0, so since I am defined that the instantaneous velocity by the tangent of this curve, why the tangent would be 0 for this curve?
Parallel to x-axis.
Parallel to x-axis. I can say the tangent at that point.
T3.
Yeah. T3 is going to
At
be
the T3 point.
Yeah.
Yes, sir.
I can say that point the tangent would be 0, and that point is the tangent is going to be also the 0. Right?
Yes, sir.
These 3 points actually for this curve, the tangent is going to be the 0. So that's when I can say in that case the instantaneous velocity is also going to be the 0 in this 3 point or the 3 time if you can find out the time. Now, what is the physical significance, the instantaneous velocity of this point? Remember, when the instantaneous velocity is 0, we say in physics the car will be momentarily stopped. We say that this point R, the particle would be momentarily stopped. The particle would be stopped over there. And that what is the explanation of that thing? Say when you driving your car, say this is you driving in that direction, and suddenly you want to change the direction. So you want to make a turn over here, say from that side to that direction. And this is the point where your instantaneous velocity will be 0 over there. At the point, the turning point, your instantaneous velocity would be 0 over here. That is the point actually. At the moment you make a turn, you instantaneously actually change your direction, then we can say that the car will be momentarily stopped at that point. Although in physically we find out the car is turning that point because of inertia of the car. But I can say that at that point the car is momentarily stopped. That is the significance or explanation of this instantaneous velocity at that point. If you find out that instantaneous velocity of a particle is 0, it could be basically the changing its direction at the point. So that's why that the car, we can say that the car will be momentarily stopped at that point. So this is actually that physical explanation. So the instantaneous velocity where it would be 0. So since we find out, so this is actually the tangent of that curve using that definition, because this is dx over dt, basically the tangent of position versus time graph. Then we can say that the tangent 0 means we say the car would be basically the momentarily stop, which means that we can say the car is basically, or the particle actually changing its direction at that point. That's how actually we can find out that instantaneous velocity. If you could find out the instantaneous speed, in that case basically we have to take that magnitude of that instantaneous velocity. All right, by the same way we can find out, say that average acceleration, that would be basically, say that if I find out that average acceleration for this journey t1 and the t2, I'll use my definition. It would be, because acceleration we define rate of change of velocity, so which is velocity t2 or minus v t1 divided by del t. So del t means actually I should write t2 minus t1, right? Then I can write, so this average acceleration would be basically that del v over del t. That would be my average acceleration. And this average acceleration, if you want to find out, say that 2-dimensional, I write down this as a general definition. Then if it is 2-dimensional, probably I'll write it would be del vx. So that's means change of velocity along to the x direction into del t I hat plus del vy divided by del t z hat. If it is 3-dimensional, I will add del v z divided by del t k hat. So that would be actually your equation of average acceleration. And remember, average acceleration is a sign sensitive. We have also considered that one. So if I say for this case that average acceleration, I can say in between time t1 and the t2 for this journey, whatever I draw over here, this one, it would be, say that it could be greater than 0. And if you think about, say, the average acceleration t1 and the t5, in that case is going to be basically less than 0 over here. You can find out in that way. And what about that instantaneous acceleration? Instantaneous acceleration. Instantaneous acceleration, by the same way we will define that any particular time. So we'll write down, say that the limit del t tends to 0, which would be vt. So the velocity at the time t, then the velocity t plus del t, which is the final velocity, divided by del t, right? So del t, actually I take the difference, t plus del t minus t, that will give me actually the del t. Then you can write, so this is actually the instantaneous acceleration of the particle at any time, that we can write down in a equation, because this is actually the definition of the derivative of that function v. I can write it would be dv over dt. It should be, if I write vector, I use the I hat over here. So, or we can also write down this thing, because we define the v actually, which is v, we write dx over dt into I hat, right? And then we can say that a would be basically d square x divided by dt square I hat. So this is would be actually that instantaneous acceleration of a particle at any time. So that's mean if you know that position function, if you take that second time derivative of that function, then you can find out that instantaneous acceleration of the particle. If it is toward the 3-dimensional, you have to add toward component. So this is dx square dt square I hat plus d square y dt square j hat for 2-dimensional. If it is 3-dimensional, I will add one more component, d square z divided by dt square k hat. So that would be actually your instantaneous acceleration of the particle, and it could be also so the greater than 0 and the less than 0, depending on which direction you are moving. Let's think about a particle is moving according to this equation. Say that x equal to 8 minus 6 t plus t square is a meter. So that's mean the particle is changing its position at different time, right? So if you plug in the t in different value of t, you will find out that position would be different. I'm going to find out, say, what would be that is position, velocity and acceleration at different time. First, if I want to find out that velocity at any time, I can write v, it would be dx over dt, right? So that's when I'm going to take the first time derivative of this equation, that would be basically 6 plus 2t meter per second, and acceleration would be, that would be basically second time derivative of that position function, right? So dx square divided by dt square, that's going to, or first time derivative of the velocity, it will give you basically the plus 2
sir.
meter per second square. And you have to say the plus 2 actually, because this plus and minus sign has a significance over here.
Okay, sir.
Yeah, don't neglect that sign. Fine. Now, if I asked you at the time t, at t equal to 0 second, so that's mean when it starts its journey, what is the x naught? X naught means the initial position when I start. Then I can say, if I plug in the t equal to 0 into that equation, I can say x would be basically that 8 meter, right?
Yes, sir.
And v naught is going to be that minus 6 meter per second, and a is independent of the time, which is 2 meter per second square. So that's when I can say it is independent of the time, means the acceleration is not changing with respect to the time. Then I can say the particle or the car will move at a constant acceleration over here, because acceleration will not change, it will be the remain same throughout its journey. That's why we will say that this particle or the car will move at a constant acceleration. Fine. Now, if I ask, look at this, when I start that journey, it is at x naught actually that 8 meter. So that's mean whatever my coordinate was, where I choose that origin, the car location is start at different point, right? When I start the countdown my time, the car is basically 8 meter away from my origin. Now, if I ask at what time it would be at my origin, or I can write say what time, say that x would be equal to the 0.
Say 3 seconds, sir.
As let's see
I-
that. So x,
Yes, sir.
if you plug in that, so I'm going to use that equation over here, only this equation. So if I plug in x equal to 0, then what I'll find, it will be basically the quadratic equation, which is 8 minus 60 plus t square, right? 6t plus t square, right? So at what time actually that it would be, the position would be basically the 0. So that's when the it would be, car would be actually at the origin of my reference frame. So that's why I plug in basically the x equal to the 0 over there. Then this is a quadratic equation. I can solve this one. If I solve, I'll find out, since it's a quadratic, t has the 2 root. One would be, t would be, if you solve this particular equation, you will find that t would be plus 2 and t would be also plus 4. I can write down this unit to be basically the second. Both two roots I have to consider over here. I cannot neglect, because this t is not negative any of this quantity, right? I'll explain what is this thing over here. Let's just take that some data from this equation. So if I ask when v equal to the 0, very simple. I can plug in this one, or I can write down this equation to find out the when velocity would be the 0, right? So I'll write down 0 equal to, what is this equation, minus 6 plus 2t. Then I can find that t will equal to that 3 second, because if I plug in t equal to 3 second, I'll find out the v would be 0, right? So that's when at t equal to 3 second, the velocity would be 0 of that car. Fine. Now, when velocity is 0, what is that x? When v equal to 0, what is actually that x? I have to find out. Fine, to find out that one, so I know if I just plug in that, I know the velocity is 0 at t equal to 3 second, right? I'm going to plug in to find out that position 3 second into that equation. I know at t equal to 3 second the velocity is 0, so that's why I'm going to plug in that 3 second into that equation to find out that displacement of that curve. So if you plug in, you will find out when v equal to the 0, x would be basically that minus 1 meter. If you plug in t equal to 3 second into that equation, you can find out it would be minus 1. Basically t equal to 3, it should be 9. 9 plus 8 is going to 17, and which is plus 17 minus 18, right? 6 into 3, that's going to be the 18. So 17 minus 18, that's going to be giving x equal to minus 1 meter. So I find out some data over here. Now I'm going to draw that one. Say if I draw this case, say this is my x direction, and say this is my t. It's a one dimension, so that's why I'm drawing that. So and I choose, so this is my positive x direction, because that's why I give that, this is the upward is positive. Fine. Say this is my 8, but this is my origin over here. So and I level the time. So this is actually 1, 2, 3, 4, 5, 6, and so on. Say this is 1, 2, 3, 4, 5, 6, and 7. And I also say this is actually a minus 1. I'm going to find out. So this is actually the minus 1. So for only for calculation, I draw this one, although my drawing is not exact. Now, when t equal to 0 second, I find out my location was 8 meter, velocity actually the minus 6 meter per second, and a was plus 2 meter per second square. So that's mean at t equal to, when I start down my count down my time, I was basically at that location which where actually that x equal to 8 meter from that origin, and in that case my velocity is minus 6, so that means velocity would be towards that direction, which is actually that minus 6 meter per second. It's a negative because right now I am moving in the opposite direction of my positive x direction, and my acceleration was plus 2 meter per second, right, which is plus 2 meter per second square, which is the opposite direction. Right now my velocity and the acceleration are in the opposite direction, so I can make a general idea that the car will be basically the slow down to move towards that origin. Fine. Now I also find out that x equal to 0 between the two time. One is actually the t equal to 2 second and t equal to 4 second. It means that t equal to 2 second, this is that point, at that point time car would be over here, and t equal to 4 second car would be also at that 0 origin, because displacement is 0 over there. Fine. Now also find out that at t equal to 3 second is position was negative x, which is that point. So that means at t equal to 3 second car must be over here. Now if I want to draw that displacement versus time graph of this journey, then you have to draw actually it start from there with a speed, is going to slow down, slowly is go in that way. At t equal to 2 second it would be at the origin, and t equal to 3 second it would be at the location of x equal to minus 1, and at t equal to 3 second is velocity is 0, so that's mean instantaneous velocity is 0. I can say it will make a turn. At t equal to 4 second it will be again at that origin, and it will go in that way. So that would be actually that journey of that equation we define in that way. And remember, this equation I write, which is actually the displacement, this is the most general equation of displacement. This is the most general equation, and this is only one equation you have to carry in your head somehow. This is one more equation I am going to give you actually. Initially I give you one idea, which is the vector triangle law, and right now I am going to give you that displacement of a particle. Most general equation of a displacement of a particle would be in a form, in that one I am going to write x equal to c1 plus c2t plus c3t square, which is a write down that equation. X was 8 minus 6t plus t square is exactly the same equation, but right now I am writing most general way, where c1, c2 and c3 basically that constant. I am going to find out that constant over here for you. Say if I take the velocity over here of this function dx over dt, what will be that? If I take the derivative of this equation with respect to the time, what I will find out? Since I consider c1, c2 and c3 is basically the constant, I know if I take the derivative c1, that will be give me the 0, right? I'll find out in that way it would be c2 plus 2
2c3t.
c3t, right? So this
Yes.
is my velocity. What about the acceleration?
So just 2c3.
It would be only that 2c3, right? Now if I write at t equal to the 0 second, I can say x naught. If I plug in the t equal to 0 into that equation, I'll find out c2 and the c3 will be vanished. I'll only find out the c1 would be x naught, right? And if I plug in the t into that point, I'll find out the v naught would be basically that c2, and c3 is basically the independent of time, so I can say this half of a is going to be the c3. Can I write this thing?
Yes, sir.
Then I can say this would be my equation, which is x equal to x naught v naught xt. I am writing v naught xt, there is a reason I am going to tell you, plus half of a t square. So that is actually the most general equation to find out the displacement of a particle. And remember, this equation is not a new for you. You find out in another way. Probably you use that equation in another word, which is h equal to ut plus half of a t square, right? Probably you are
Yes, sir.
familiar with this equation. It is exactly
Yes.
the same equation. When you use this equation, you already assume that your car will be always start from your origin. In that case, you consider x not actually the 0. That's why you find out this equation, but which is not true. You are not always start from your origin in your journey. You could be start from different position from your origin. So that's the thing I show you in that example. So that's why the all other equation you know actually h equal to u2 plus half of t square, v equal to u plus at, or v square equal to u square plus 2ax, that all equation could be derived from here. Because I find out, look at this, if you take that first time derivative, you will find out that velocity which is this one, right? If I take, look at this, first time derivative, if I take this equation to find out that velocity which is dx over dt, that will give me x naught will be 0. I'll find out v naught x plus is going to be at, because if you half of t, if you take the 2, it will be the 2t, right? If you take the t square, it is going to be the 2t. Then 2 and half will be cancelled out. So I'll find out this equation. V would be v naught x plus at, which is exactly that equation, v equal to u plus at, where v naught x actually my initial velocity in the x direction right now. So that's why I write down the subscript as a v naught x. This x indicating this is the initial velocity in the x direction, because I have to dealing with the 2-dimensional and the 3-dimensional case also. That's why this is the most general equation I'll write. So this is will be motion x naught plus v naught xt plus half of axt square. If it is towards the y direction, I'll write in a form y equal to y naught v naught yt plus half of ayt square. If it is as 3-dimensional, I'll write down the same equation in the z direction, v naught z t plus half of azt square. So that's been only this equation. I'm saying that this is, guys, the most important equation right now. I will use only this equation, whether I'm going to 1D, 2D, free fall, even the projectile motion, I'm going to explain only by this equation, because this is the most beautiful equation, most easy equation, and one of my favorite equation in this physics, because using this simple equation, I can explain any type of motion. So that's why I'm giving this equation right now over here. I will use only this equation right now, starting from this class. I will use this equation up to the fluid motion. Even the fluid motion, I am going to use this equation. Any type of motion actually, I can use this most general displacement equation. Using that one, I will explain every type of motion. So that's why, guys, I'm giving this equation. It's a very important equation. The equation you actually know, which is very special kind of equation. I'm not going to recommend that one, because that equation is not going to work in every time. But this equation, you can explain any type of motion. You can explain whether the particle moving at a constant velocity or not, constant acceleration or not. You can explain by that form equation. Can anyone say whether, say, if the particle is moved according to this equation, say that x dot v naught xt plus half of a t square, whether the particle moving at a constant velocity or constant acceleration or neither not?
So it is moving with an acceleration, but it is maybe a constant acceleration, sir.
Maybe constant acceleration. All right.
Yes.
Is there any other want to say something?
Sir, it is constant acceleration
It is constant acceleration. That's right.
because it is not dependent on the x position.
X position. Could you be more precise?
Sorry, sir. X position, not the x position. X direction.
X direction. Yeah. Can it? What about the mathematician? What is so? Says what would be your explanation if it is moving at a constant acceleration? Or what we can say from the mathematical point of view actually? Why I will say it will be moved at a constant acceleration? Hmm?
Because the rate of change will be always same, sir.
Exactly. So
For
that
x.
means if you take the second time derivative of this function, if I write dx over dt, second time derivative, basically I'll find out that t is going to be the independent of that t. Say if I take the first time derivative of this function dx over dt, I'll find out that would be my velocity, right? So v, which is going to be v naught x plus at, right, which is my velocity equation, but is still that velocity as a function of t. It means that if you change the time, your velocity, final velocity will be the different. So that's mean it is changing its velocity at different time. So we cannot say that the velocity will be constant. We define any constant function that is not changing with respect to the time or any other parameter, right? So,
Yes, sir.
but if you take the second time derivative, a or first time derivative of the velocity, which I'll find out,
You will be cancelled out.
it will be, this will be constant, it will be going to the 0. I'll find out only the a, which is
Yes, sir.
independent of the time right now, right? It's not
Yes, sir.
depend on the time. So that's why I can say that the acceleration would be the constant over here, right? What if, say, if the particle is moving according to this equation, say x naught v naught xt plus, say that half of a t cube.
Sir, it is not a constant acceleration
Right. So if you take the second time derivative,
because it is dependent on t.
t, yeah, exactly. If you take the second time derivative, this one has a power is 3. After taking the second time derivative, there will be also a t present in your equation.
It will be a3t.
A3
3
plus 3 by, so something would be like that, right?
Yes, sir.
So,
yes, sir.
So that's mean it will be some constant over here, then you will find out as a function of t. It means that right now the particle is not moving at a constant acceleration. If you change the time, the acceleration will be the change. So that's why we can say whether the particle is moving at a constant velocity or constant acceleration or neither not, looking into just this general displacement equation. You will find out. I'll do some problem. We'll see that in the next class actually. So that's why this is most beautiful equations. Come on guys, cope up with this equation. I will write down any type of motion with that format. Half of ax, sometime I will write down ax. If this is there is two-dimensional acceleration, it t square. That would be that most general equation for the displacement. I will use only this equation. So that's why whether I'm going to say that the free fall or any other motion, I'm going to explain by this equation. Even the projectile motion I'm going to explain with that equation. All right, so one more case actually I'm going to talk, say I'm going to draw that curve of this motion. So first I'm going to talk about, say that constant constant velocity over here. So if I say a particle is moving at a constant velocity, what would be that velocity versus time graph? Say that velocity, this is be the time. What would be that
So
curve?
parallel to the x-axis.
Parallel to the
A
x-axis.
straight line.
Hmm?
Yes, sir, like this.
This is the case, right? Parallel to the x-axis. So that's mean every time if you increase
Yes,
your
sir.
time, the velocity is not changing. That's mean that velocity is remain constant over here, right? So I should use that one.
Yes, sir.
All right. So what about, say that acceleration versus time graph?
So it will be 0.
0, sir.
So this is actually acceleration. So definitely the curve will be over here,
Yes, sir.
right?
On the x-axis.
On
Yes,
the
sir.
x-axis. What about, say that displacement versus time graph?
Sir, sir, for a constant velocity, it will be it will just get us a slope, sir.
Yeah. So what would be that equation? So how I'm drawing this
X
one?
equal to VT, sir.
x equal to vt, exactly. Look at this. So I said my general equation actually x equal to x naught v naught xt plus half of at square, that equation, right? So if it is moves at a constant velocity, then your acceleration is 0, right? Right?
Yes, sir.
Your
Yes, sir.
acceleration is 0. Then your equation become x equal to x naught v naught x into t, which is actually a straight line equation, right? Y equal to, I can say, write down the x naught, actually basically the
Mx plus
constant,
c.
mx
Yes,
plus
sir.
c, right? So if you consider, most of the case actually, when you say that a particle moves at a constant velocity, you say s equal to vt equation. I can find out that equation if I say, in my equation, if I say x not equal to the 0, which is the special case you consider, your car will be always start from your location, you choose the origin, but that's not the real case. Then if I choose the x not
Sir,
actually the
can we
0,
consider s is equal to x minus x naught?
if I consider in my equation x not equal to the 0, I will find out this equation x equal to vt, which is exactly the same equation s equal to vt.
Sir,
Yeah,
sir, can we consider s is equal to x minus x naught?
s minus s naught, yeah, exactly the same thing.
No, sir, x minus x naught.
Yes,
S
the
is
same
equal
thing.
to x minus x.
Yeah,
Yes,
yeah,
sir.
that's true. So you can write down this. You're saying that it would be half of ax t square. You're saying that x minus x naught actually v naught x t plus half of ax t square. Right, it's the same thing. So you're saying that in
Yes,
that
sir.
case x minus x naught actually the s. Then you will find out it's the same equation.
Yes, sir.
Right. So that's it. So that's
Yes,
why.
sir, I understood.
Yeah, if you write down this equation, actually in that case I'll find out this displacement versus time graph would be this one, where if you take the slope you will find out this thing, which would be your v naught x, right? That
Yes, sir.
slope. And this one is going to be basically your x naught, which is actually that c we use in our straight line equation, right?
Yes, sir.
That's fine. What about, say, right now go for, say, that constant acceleration, constant a. I can say my acceleration versus time graph would be any constant function. Hey, it would be that. It should be the straight line. I'm sorry, my drawing is not exact. This will be the case. It's a acceleration versus time graph, right?
Yes, sir.
What will be velocity versus time graph?
Sir, it will be a straight line
Yeah,
which has a slope.
this has a slope, exactly.
Yes, sir.
So if I write, say that this way, v equal to v naught plus at, in that case I will say this one, right? This would be my
Yes, sir.
a slope, and this would be my v naught. If v naught actually the 0, then it will be passes through that origin. This one actually this equation, and this one will give me v actually at. In that case actually that v naught actually the 0. So that means it is start
What
from,
c is equal to 0.
yeah, initial velocity actually the 0. It is start from the 0 actually. You can find out in that.
Yes, sir.
What about displacement versus time graph?
So it will be a curve. I think it's a kind of parabola.
It's a kind of parabola. So this is the time, say this is my displacement. So it will be like that actually. That,
Yes, sir. Yes, sir.
right? Why it is come so? Look at this. This is my equation: x naught v naught xt plus half of a xt square. If I consider initial velocity is 0, initial displacement is 0, then I'll find out x would be basically half of a xt square. Since it moves at a constant acceleration, I can say this total term actually is basically the constant, right? Then actually it is
Yes, sir.
x directly proportional to t square curve. So that's why this would be
Yes, sir.
actually the
Yes, sir.
displacement versus time graph. Right. What about the
Yes,
case
sir.
for the free fall? What about the free fall? Is the my time is over?
G is constant.
Yeah, I'll talk about for the free fall in the next class because your time is over. So thank you very much.
So what about the attendance?
Yeah, give your attendance, right? Just write your ID right now. Only for ID. Remember, do not write down anything else. Just your ID. If you write down there something else, then you will not get your attendance because I'm not going to give you attendance manually. I'll just copy that thing and I'll paste into my is a program Excel sheet. It will only can read your ID. Do not write anything else in front of your ID. Just write down your ID.
Sir,
Yep.